Noise. In audio and video systems, the electrical disturbances are appearing as an interference that is called as noise. Noise is an unwanted signal that corrupts a desired message signal. And in general, the noise may be predictable or unpredictable, that is random in nature. The noise is having two types. One is predictable, another one is unpredictable. The predictable noise can be estimated and eliminated by proper engineering design. For example, power supply gun and ignition radiation pickup and spurious oscillators in feedback amplifiers and fluorescent lighting are the examples for predictable noise. And the predictable noise is generally man-made and it can be eliminated easily. And the unpredictable noise, it is varies randomly with time, and we have no control over this noise. And in the absence of noise, the identification of message signal at the receiver is perfect, and also the presence of noise complicate the communication system. And the term noise is generally used to represent a random noise. The sources of noise are external noise and internal noise. The external sources of noises erratic natural disturbances and man-made noise, and internal sources short noise and thermal noise. The external noise created outside the circuit. Example, the erratic natural disturbances are this kind of noise occurs randomly and it is caused by lightning, electrical storms, and other atmospheric disturbances. And this noise is predictable in nature, and this noise is also known as atmospheric noise or static noise. And atmospheric noise is less serve above 30 megahertz. And the second one, man-made noise. This noise occurs due to undesired pickups from the electrical appliances such as motors, switchgears, and automobile and aircraft ignitions, etc. This kind of noises is under human control and can be eliminated by removing the sources of noises. This noises is effective in the range of 1 MHz to 500 MHz. The internal noise is created by active and passive components within the communication system. This noise is also known as fluctuation noise. It is caused by spontaneous fluctuations in the physical system. For examples, for the fluctuations are thermal motion of free electrons inside the resistor known as Brownian motion, and the random emission of electrons in the vacuum tubes, and the random diffusions of electrons and the holes in the semiconductor. The two types of fluctuation noises are short noise and thermal noise. The short noise present in active devices due to the random behavior of the charge carriers, and the electron tubes short noise will generated due to the random emission of electrons from the cathodes. This is the current variation of short noise. So I of t is the total current, In of t is the fluctuations of current, and I naught is the variations in the current. And the current fluctuates about a mean value I naught, and the In of t which wiggles around the mean value is known as short noise. The total current I of t is expressed as I of t is equal to I naught plus In of t. So I naught is a constant mean current and In of t is a fluctuating current noise. And the power spectral density spectrum of the statically independent non interacting the random noise current In of t is given as Si of omega is equal to Q into I naught. Here Q is the electronic charge, that is Q is equal to 1.59 into 10 power minus 19 coulombs, and I naught the mean value of the current in amp. The power density spectrum in the above equation is frequency is independent. This frequency independence is only up to a frequency range which is decided by the transit time of an electron to move from the anode to cathode. After this frequency range, the power spectral density varies with the frequency. It is shown in the figure. The first figure is the power density spectrum, and the second figure is bandwidth of measuring the system. And the transit time of an electron in the diode depends on anode voltage P, and it is given by tau is equal to 3 into 3.6 into d divided by root p milliseconds. Here d is the spacing between the anode and cathode. At an incident in the diode, d is equal to 2 millimeter and v is equal to 40 volt. We have the tau is equal to 10 power minus 3 microseconds. In figure, the power density curve may be considered a flat close to origin. And for example, modulus of omega tau less than or equal to 0.5. Hence, SI of omega can be considered constant up to modulus of omega tau is equal to 0.5. For transit time tau is equal to 10 power minus 3 microsecond, the maximum frequency up to which the power density SI of omega remains constant is given as omega is equal to 0.5 into 10 power 9, that is equal to 5 into 10 power 8 radians per second. It is equivalent to a linear frequency f is equal to omega divided by 2 pi, that is equal to 80 megahertz. Hence, for all practical purposes, the SI of omega is considered as frequency independent below 100 microseconds. It is shown in the Schottky formula. The mean square value of the randomly fluctuating noise current will be given as In square, that is equal to 2q I naught into del f, where 2 del f is equal to bandwidth of measuring system. The above equation is known as Schottky formula. In some cases, the electronics interact with each other during this moment in the space charge limited region of thermonic diode. In such cases, power density spectrum is given by SI of omega is equal to alpha into Q I naught. Here, alpha is the smoothing constant. The range from alpha is 0.01 less than alpha less than 1. The smoothing constant alpha depends on the tendency of interacting the electrons to smooth out, and gives a constant current alpha is equal to 1.288 K into Tc into Gd divided by Q I naught. K is a Boltzmann constant. The value is 1.38 into 10 power minus 23 joules per Kelvin, and Tc is the cathode temperature in the degrees Kelvin, and Gd is the dynamic conductance of the diode. We can substitute this equation number 5, the alpha value into 4. SI of omega is equal to 1.288 K into Tc Gd divided by Qi naught into Qi naught, where here Qi naught will cancel. So SI of omega is equal to 1.288 into K into Tc into Gd.